this is Olivia over at Prepaze, and today I will be presenting our second part in our functions unit. So last time we defined our functions using some examples, that a function is an equation that defines a relationship between an independent and a dependent variable. I used the relationship between unglazed donuts and glazed donuts entering a glazing machine to illuminate this definition. However, there is one more stipulation that defines a function, because not every expression that we'll ever make will be a function. So let me share with you the extra part of our definition. For every input, there is only one output. This is our extra stipulation for a function. And let's check and see if my pitched function for our relationship between our glazed and unglazed donuts applies, and we can define it as a function. So I suggested that our relationship was defined by the function y equals x. Is it a function? Let's check. For every one input that we have for x, or the number of unglazed donuts, is there only one output for the number of unglazed donuts? Let's check. So if I say I made 10 donuts, it looks like I only have one response. I have 10 glazed donuts that I made in response to only having 10 unglazed donuts. Let's check at 40. Do I have only one corresponding output? Yes, I do. For 40 unglazed donuts, I will receive 40 glazed donuts if I'm using my function properly. Now, going through and checking multiple times is an accurate strategy, but here's a little tip and trick that will help you check any function that you want to qualify and define as a function. This is called the vertical line test. So you're pitching a function, an algebraic expression, and I want to see if it qualifies, it matches with our definition. So we check with the vertical line test. We graph our function. For example, I picked y equals x, and if I drag a vertical line over my graph from start to finish, is there any time that my vertical line is intersecting with my graph more than once? For y equals x, I'm only hitting at one point on the graph of my function at any given point. It's along that line. Let's check some other ideas and other expressions and see if they also match with this functional definition. The second equation that we made together in the last video was defining the height of individuals on a roller coaster. And this was the graph that I made. I said y is equal to negative x minus 10 squared plus 100. And let's check with our graph and see if it passes our vertical line test. Here's my vertical line. I'm going to drag it over the equation, the graph of my expression. And as I check, I'm only hitting, again, only that one spot on the line as I drag my vertical function over. And I should assume that this pattern should continue over infinity. Now, what would an algebraic expression look like if it was not a function? So this graph is an example of an equation that defines a relationship between an independent x and a dependent y that would violate the terms of our vertical line test, or the second qualification for a function, meaning that for any one input, there's exclusively one output. Let's drag our vertical line test over. So here's my vertical line. As I'm going at 0, I'm fine. I'm only hitting 1 point. Let's move over one piece. As you can see, I'm hitting at the red line and the blue line for the rest of time. I'm hitting this graph twice, and this would be a violation of our function agreement. So even though it is an expression that we can write, we would not define this as a function. Believe it or not, another common example of an equation of a function or an expression that does violate our functional agreement is going to be a circle. So here is an equation of a circle that has a radius of 3. And as I drag this line over, even though at first I'm only hitting at one point with my vertical line, for every other point for the completion of the circle until I hit the end, I'm hitting it twice. So the equation for a circle is not an equation of a function. Thanks for joining me, guys. I'll see you in the next video.